Hi there and welcome back to ESMARConf 2023. This is the 6th presentation session on data visualization and communication. As always, you can ask questions via Twitter by following @ESHackathon or using the Slack channel if you've registered for the conference. Presenters will be answering the questions after this session as well, so keep an eye out. Up first is Theodoros Evrenoglu, and he's going to be introducing metaCOVID, a web application for living meta-analyses of COVID-19 trials.
My name is Theodoros Evrenoglu, and today I'm presenting to you the metaCOVID sign application. That is a web application for living meta-analysis of COVID-19 trials. metaCOVID was created in the concept of the COVID-NMA initiative. That is an international project which performs a living systematic review of COVID-19 trials. COVID-NMA was created since the early days of the COVID-19 pandemic with 3 main pillars. First of all, to continuously collect, critically appraise all the available evidence related to COVID-19 interventions. Then, to synthesize the available evidence through meta-analysis, and finally, to make the results publicly available through the COVID-NMA platform. For almost 3 years now, the COVID-NMA data extraction team was identifying on a daily basis new trials through the LOVE and the Cochrane COVID-19 study register platforms. All this continuous work has led to a huge amount of available information in our database. Up to March 2023, the COVID-NMA database was consisted by 572 trials that were investigating 332 treatment comparisons and 63 trials investigating the efficacy or safety of 27 vaccines used against COVID-19. All the data for the different pairwise comparisons in our database are pulled through meta-analysis and are summarized with forest plots that are a standard way to summarize meta-analytical results. These forest plots are then uploaded in the COVID-NMA platform. The analysis takes place using some very specific settings that are defined in the COVID-NMA protocol. For example, that we use a random effect inverse variance model to synthesize our data, or that we use the restricted maximum likelihood method to estimate the heterogeneity parameter. These specific analysis settings create a consistent environment in order to do the analysis, but on the other hand, it is creating our results to be non-amendable. And we know that with such a huge amount of available data, special analysis topics will inevitably arise. For example, we know that across all the trials with hospitalized patients, the risk for serious adverse events is only 8%. This refers to the trials in the COVID-NMA database. So this implies that serious adverse events is a rare outcome, and we know that in such cases, the inverse variance model can be problematic. In fact, from the literature, we know that in such cases, alternative models should be used instead of the inverse variance. Beyond the different statistical issues that might arise, we were in the situation where stakeholders and different guideline developers that were using the COVID-NMA platform wanted additionally to investigate our data. They wanted, for example, to investigate the impact of the trial characteristics in the results, and they wanted to produce their preferred evidence summaries. Overall, though, accommodating these special needs through solely the COVID-NMA platform can be challenging, as it will render the output in the platform very confusing for the different users. To accommodate these special needs, we launched and made freely available the metaCOVID application. That is an R-Sign application for which the calculations are mostly based to the Meta4R package. This application allows for a real-time analysis of the COVID-19 trials for both treatments and vaccines based on the COVID-NMA database. Through the application, the users can modify the analysis in several different ways. For example, they can modify the type of the meta-analytical model, they can modify the method for estimating the heterogeneity, and they have also some other options. The output of the application is again a forest plot that the user can download and use for their own personal needs or their own scientific projects. Let's have a look now and see how the users can use metaCOVID in practice. So once the users enter into the application, they are introduced to the home page that we usually use in order to do some announcements related to the functionality of the application of the COVID NMA database. The two basic analysis options in metaCOVID are connected to the menus related to the COVID-19 treatments or the COVID-19 vaccines. I will focus today on the COVID-19 treatments because the analysis options in the COVID-19 vaccines are almost the same like the treatments. So here are the different options that are available in this panel. The first thing that the users are asked to do here is to make a choice of a treatment comparison of interest. By clicking this menu, we see that we have different and several available comparisons, which are organized in terms of their treatment type that is stated here with bold letters at the top. Today, I'm going to choose the comparison between corticosteroids versus either standard care or placebo. The second thing that the users are asked to do here is to make a choice for an outcome of interest. In total, metaCOVID can contain data for in total 13 outcomes of interest. And today I'm going to choose the outcome of mortality at day 28, as I think that this is a very interesting outcome. So by choosing a treatment comparison and an outcome of interest, the metaCOVID application is producing a forest plot based on those two choices. Here we can see that this is a forest plot that contains all the basic elements that we are used to find in forest plot that summarize meta-analysis results. For example, we see the study-specific data, and of course, we see at the bottom the overall summary result printed in the form of a diamond. However, the forest plot in the metaCOVID application is also enhanced with some additional characteristics. For example, we can see that the studies are also grouped according to the severity of the included patients. And we have the subgroup of the studies that contain patients of mixed severity and the subgroup of studies that contain patients of critical severity. A subgroup analysis takes place within those subgroups, and the subgroup-specific diamond is also printed within the forest plot. Additionally, all metaCOVID forest plots contain a risk of bias assessment that is related to each one of the studies that can be found in our forest plots. The assessment of the risk of bias is done by a team of experts working with the COVID NMA project and using the Cochrane ROB2 tool. Additionally, we can see that at the bottom of the forest plot, we have also some reports about the heterogeneity that refers to the overall analysis. And whenever we have more than one subgroups in the forest plot, we have also the test for the subgroup differences posted at the bottom. Until now, the analysis is done only by choosing a treatment comparison and an outcome of interest, and by retaining the rest of the options in the default form as they are in predefined. However, the users can modify these predefined options and they can bring the analysis in the form that they want. For example, they can change the heterogeneity estimator and use another one. For example, they can use the Sydney-Bjorkman estimate in order to do this analysis, and you can see that immediately the output for the heterogeneity report changes. Additionally, they can change, for example, the subgroup criterion and deviate from the default choice of grouping the studies according to their severity. Here, I will choose, for example, to do the analysis based on the conflict of interest status of each study, and you can see that the forest plot again updates and groups the studies according to their reported conflict of interest status. And of course, we can see that now we have a diamond for each respective subgroup. In this forest plot, we can see additionally that we have some studies reporting high risk of bias, and of course some users may want to exclude those studies from the analysis. This can be done easily by clicking the respective button, and we can see that again the forest plot immediately updates. There are several other options. I will demonstrate another one. We can use metaCOVID in order to deviate from the default choice of the inverse variance model and use some alternative models by clicking this button that refers to a sensitivity analysis using different models. When we do that, the results are summarized in the form of a table, and we can see that here we have the results in terms of alternative models such as the Mantel-Hansel or the Pito methods. So this is how the metaCOVID looks like and how it can be used in practice. I'm going to go back to the presentation now and summarize. So as I told you before, metaCOVID is an application that allows all the users of the COVID-19 platform to interact with our database. The primary analysis can be modified in many different ways through the application, and the users can download the forest plots and in order to use them for their own projects. Of course, there are disadvantages on the use of the application. For example, the users cannot upload their own data. Of course, all this user-friendly environment does not guarantee the proper interpretation of the findings. Overall, metaCOVID appeared to be a helpful application. Many stakeholders and guideline developers have declared their engagement with the application, and this translates into numbers because according to the Matomo tracker, the application has on average 140 unique users per month. Before I close, I need to mention that some more details can be found in our open access publication at Research Synthesis Methods. Thank you very much for your patience. I'm happy to take your questions now.
Thanks very much, Doris. Up next we have Lukas, who's going to be talking about creating interactive ShinyApps meta-analyses
with metaUI.
Creating interactive ShinyApps for meta-analysis with metaUI. There is no straight path from the data that you collected for your meta-analysis to the results. It's rather a labyrinth through many different choices. Should you exclude certain outliers, how to deal with different effect sizes, and which type of model should you choose? These choices affect the results in critical ways, and meta-analyses have been often criticized for choosing one path over another. In practice, researchers usually have one planned or even pre-registered path that they take, and then they add a few more analyses such as robustness checks or some analysis for exploratory purposes. But still, according to other researchers or reviewers, there is often a path missing. So, how can we do justice to the large number of equally justified but different paths? What we have observed so far are three approaches. First, in what we call the shotgun approach, all types of analysis that make more or less sense are shot at the data. This typically yields a very large table in the manuscript, as you can see on the right. Second, some researchers have run a multiverse analysis. That is, they first conduct many different meta-analyses and then they run a meta-analysis on the results. The third approach, which is what we have been focusing on, is what we call the open box. Thereby, you provide others with your dataset and tools to run all sorts of different analyses. What if we exclude effect sizes plus minus 2 standard deviations? What if we only take studies that feature a cover story? How do the results change if I filter out non-pre-registered studies? Can you tell me what effect size you get with a selection model? Sure, the open box is a published ShinyApp that allows everybody to access the dataset via a website and explore and download the original or filtered dataset. The open box approach is simple, as anybody can go on the website and start analyzing. It is also flexible. A researcher once asked us why we chose to report a P-curve but not a Z-curve. At that time, we had not really been aware of Z-curve, which is why it wasn't there yet. So noting that this would provide us with additional information, we simply added a Z-curve analysis to our ShinyApp. So if you can do it in R, which is the case for pretty much everything, I guess, then you can also feature it in a ShinyApp. The downside, however, is that creating ShinyApps is a bit difficult. And to overcome this problem, we created an R package that creates the ShinyApp for you. Make sure to check out the tutorial at ESMARConf on how to use our package, but in a nutshell, these are the steps that you need to go through to create a website where you and others can interactively analyze a meta-analytical dataset. To let you know how easy this is, I would like to give you a brief look at the code. Again, we're still at an early stage, so more functions may be added soon and things might look a bit different later on, and everything is also discussed in depth in the tutorial. So your dataset goes up here. Then we need to know what the effect size and standard error variables and so on are called in your dataset. And you can determine the filters or moderators that you want to apply. Here we have prereq, which includes information about whether or not a particular finding was pre-registered. We also have demographics, such as the mean age, and the app will later see the range of these variables and lets you pick a value along it. In practice, you might have downloaded data from a meta-analysis that is a few years old, and you added a couple of new studies that have been published since, and now you want to know whether including the new studies affects the results, or maybe whether the new studies differ from the old studies. So you could just create a variable indicating whether or not a finding is new and put it right here, and the app will analyze whether this moderates the effect size or not. So the second function needs the formatted dataset. You can also customize labels, and you can even decide whether you want to launch the app or whether you want us to save the entire Shiny code on your computer so that you can customize it, for example. So here's an example of the Shiny app that includes an anchoring dataset. And before we get results, we have to filter or apply our filters. And here you can see the mean age, which is the lowest mean age in all of the data sets included here is 18.8. And now we may want to select only items where the scale type was open or visual. And so we have selected the filters, and now we have to click on Analyze Data. And here you go. We currently have effect size estimates from several different models below here, and a small sample description. And now let's continue conducting some moderator analysis. And again, as you can see, the app recognized that this is a metric variable and creates the plot and the table accordingly. But now we might want to know whether the scale type has an effect on the effect sizes. This is a categorical variable, and here it is significant with everything that you would need to know for reporting this. You can also download the dataset, and it will save the filters that you applied while it's still the entire dataset. And then you can update it later on to continue where you left off. So this was just a small excerpt from the analysis that you can run with the metaUI package. Currently you also get a sample breakdown with respect to the moderator variables, a forest plot of all included effect size, a funnel plot with Lagisz test, p-curve, z-curve, and information about the effect size distribution. So thank you for joining us for this presentation, and we are looking forward to your thoughts on this.
Thanks so much, Lukas. Daniel Noble is going to speak next about making orchard plots for meta-analysis.
Great. Thanks, everyone, for coming out to my talk. So my name is Dan Noble. I'm a senior lecturer and future fellow at the Australian National University here in Canberra, Australia. So what I want to overview today very briefly and very quickly is the orchard package that we developed a couple years ago. And more specifically, I want to introduce you to version 2.0, which has a number of substantial improvements over 1.0. Now, given the time limitations, I'm not going to live code, but I provided you with a vignette of sorts to allow you to move through and understand Orchard's functionality. And I'll post this the link to this vignette on the video, but basically it'll tell you here how to install the Orchard package It'll direct you to the GitHub page, which is hosting it because it's currently not on CRAN. And it just sort of emphasizes the need to make sure that you have an updated version of R because it'll be needed to play well with the EM-means package for Orchard to work. Okay, so what are Orchard plots? So Orchard plots are plots of meta-regression models. They're force-like plots, so to say. And they're specifically interested in predicting the meta-analytic mean within levels of a particular moderator in a meta-regression or multi-level meta-regression model. So just to give you an idea of what Orchard plots are, I'll introduce you to this LIM dataset, which comes with Orchard. And this is a study done by Nat Lim, Al Senior, and Shinichi Nakagawa, looking at the correlation between offspring number and size and mother size offspring trade-offs. So we can fit a meta-regression model normally using the metaphor package and its RMA.mv function. Orchard requires you fit meta-regression models with metaphor objects. It only takes metaphor objects, so you'll need to use metaphor, but that's okay because metaphor is an incredibly versatile, flexible, and very powerful meta-analysis package. So if you fit that model and we're interested in trying to predict the meta-analytic mean across different phyla, you can generate an Orchard plot quite easily by basically feeding in the model itself along with a specification of the mod argument, which tells Orchard plot which moderator you want to plot. You feed it the data and a group. The group is needed to specify the sample size for the groups within the brackets here. So this could be study often, and that can differentiate between K, which is the total number of effects. So from that, there are a whole bunch of different options here. You can transform it if it's a correlation coefficient or ZR to a correlation coefficient, which is what's being done here. You've also got colorblind friendly plotting options, in which case, because we have so many levels, I've suppressed here. And what you get then is a nice Orchard plot, which depicts the meta-analytic mean, these dots here, their 95% confidence interval and the 95% prediction interval, along with the raw data in each one of these levels of phyla. These data are weighted by their sample size in this particular instance, but it could be precision. It just depends on what you're interested in plotting. Now, one of the nice features is the ability to subset. So you'll notice here, there's a lot of data, a lot of levels where there's very little data, where we can get around that because the EM-means package allows us to make predictions at certain levels. And so what I want to show you here is how you can subset the data to certain levels, and also how you can use another function called mod results to capture the model output in a table, which can be useful for publications. So another way to specify this is using the mod results. And here, mod results takes the exact same arguments that Orchard plot does on its own. But here, for this particular situation, it will capture the model results in a table. Again, we'll feed in the phylum information, but this time we have a new argument called @, and this allows us to make predictions at particular levels of moderators in the model. In this case, we want Chordata, Arthropoda, and Mollusca, because those are the levels where we have most of the data. And not only then do we get LIM MR results as a table, we can feed that into Orchard plots to generate the Orchard plot itself, where we have the meta-analytic means and confidence and prediction intervals for each one of the levels where we have sufficient amount of data. Of course, you can then use this mod table, which is held in the LIM MR results object, to produce a nice table of those mean estimates and confidence intervals. Now, often when we have meta-regression models, we're interested in plotting continuous variables. This is less common in meta-analysis, but still reasonably common if you think about requiring or looking at publication biases like time lag bias when you're interested in year. And we can easily capture that using the bubble plot function. Bubble plots then allow you to, they take again, the same arguments, but they allow you to plot a continuous moderator, in this case year, and you can have an interaction with other different categorical levels to understand how those moderators vary within those categories differently. So this is just an example of an orchard plot. And again, we've effectively just fed it in the same sort of arguments that orchard plot takes. Now, Orchard's great because when we rely on the EM_means package, it means that instead of a single moderator multi-level meta-regression model, we can take multi-moderator regression levels, and we can basically marginalize means across different levels of other moderators. So, for example, if we turn to a different data set, this is a fish data set from O'Day et al., which was published in 2019. They fit much more complicated meta-regression models where they've got different trait types with varying degree Celsius differences between treatments and different experimental designs. So here we can just fit all those moderators in this meta-regression here, and you can see it can get quite complicated. This is the output from that model. But what we can do here is, because we have those at and by arguments built into orchard plot, we can basically set the predictions up so that we predict, say, at 5, 10, and 15 degrees Celsius differences between the treatments. And we can then marginalize over all the other elements or moderators that are in that model. Okay, and so this is basically an example of the kind of orchard plot you'd get where you're predicting the degree differences. So if I had a 5 or 15 degrees Celsius difference between your two treatments, what would be the anticipated change in effect size magnitude in each of the different trait categories. Now, one thing that you'll notice often in meta-analysis, particularly with subgroups, is that the variability in those subgroups can vary quite a bit. And this violates the homogeneity of variance assumption. We can actually relax that in Metaphor models. Metaphor has a great option here by including a category or moderator within the random effects, which allows us to estimate depending on what level. In this case, it's a different residual variance across the different trait levels. And again, we can feed that model in, and here it will then recognize that this is a heterogeneous variance model, and it'll plot variances differently across the groups depending on what the best estimate of variability is in those groups itself. Now, that's just a brief introduction to the package. Obviously, I don't have a lot of time in 10 minutes, but there are a number of other features like I-squared and R-squared functions that allow you to calculate both point estimates and bootstrapped estimates of I-squared and R-squared, as well as submerge function, which allows us to take different mod results objects and merge them together to create a single orchard plot as well. If you want to find out more, check out the vignette, which goes through quite a lot of detail, and I'm happy to take any kind of questions you might have about Orchard 2.0. On that note, thanks for listening and hope you find it useful.
Thanks very much, Dan. Over to Georgios Seitidis next, who's going to talk about graphical tools for visualizing the results of network meta-analysis of multi-component interventions.
Hello, welcome to the presentation. My name is Georgios Seitidis. I am a PhD candidate at the University of Joanna, and in this talk, I'll present graphical tools for visualizing the results of network meta-analysis of multi-component interventions. Network meta-analysis is an established statistical method for synthesizing evidence from studies that compare multiple interventions. Networks usually include interventions that consist of multiple and possibly iterative components, such as the characteristics of the intervention, the mode of delivery, if it is delivered face-to-face or remotely, individually or in groups, the type of provider, the location, etc. These interventions are referred in the literature as multi-component or complex. When they are present, the interest usually lies on the identification of the best component. To answer this question, The component network meta-analysis is commonly used. However, component network meta-analysis assumes additivity for the component's effects in multi-component interventions. This is a strong assumption and sometimes is hard to defend. It is even harder when the network is sparse, and this is because the summary estimates of network meta-analysis are mainly informed by direct evidence and are prone to confounding. The objective of this work was to develop novel ways of visualizing the network meta-analysis results of multi-component interventions in order to help the analyst to identify which components work or do not work more easily. Also, we intended to explore the behavior of the components in order to identify the most promising ones. This was done by associating the presence or the absence of components with efficacy or effectiveness. Due to time constraints, I will only present 5 out of the 8 visualization tools that we have developed. To demonstrate the usage of the suggested tools, we will use an example of a network that compares the effectiveness of self-management interventions on reducing the levels of glycated hemoglobin. Interventions are masked as these results will be submitted soon to a medical journal and cannot be revealed beforehand. The network consists of 461 studies and includes 97 nodes and 11 components. Moreover, most comparisons involve node A, which is a control group, and it will be used as a reference in the network meta-analysis model. As you can see from the network plot, there are many nodes, many comparisons, but few head-to-head studies. Therefore, the assumptions of network meta-analysis and component network meta-analysis will be challenged due to the sparsity of the network. Exploring the geometry of the network is essential, especially when you are dealing with large networks with complex structure. Component descriptive analysis can assist in achieving this goal. By visualizing the component's frequency in a colored cross table, the analyst can easily identify the most frequent components or combination of components in the study arms. Each element denotes the number of study arms where the corresponding component or combination is part of the intervention. Diagonal elements refer to components, and in parentheses the proportion of study arms that include the underlying component is presented. Off-diagonal elements refer to combination of components, and in parentheses the proportion of study arms with both components out of those study arms that include the component in the row is presented. For example, the element that corresponds to column E and row H indicates that 133 study arms include these components, but also that component E is always included in the interventions that include component H. To identify more easily the most frequent combinations, the table is colored based on the relative frequencies. The more it turns the color, the larger the percentage in the parentheses. Therefore, dark red colors indicate large percentages. From this figure, we can see that the most dark red colors were observed in the column E. This indicates that component E was almost always part of the intervention. We can also explore whether the inclusion or exclusion of a specific component impacts on the outcome. The leave one component out scatter plot identifies a pair of interventions that differ by one specific component. Here is a scatter plot for the set of interventions that differ by component B. Axis Y displays the NMA effect estimate for the interventions that do not include component B, and axis X when component B is included. Dots close to the line of equality signify no impact on the outcome. Dots above this line indicate that the NMA effect estimates are larger when the component is not included in the intervention. Therefore, for beneficial outcomes in which small values are considered as bad values, dots above the line indicate that the inclusion of a component hampers the intervention effect, while dots below this line signify a component that decreases efficacy. The opposite holds for harmful outcomes. Another feature of the scatter plot is that we can visually evaluate additivity and assumption. Additivity implies that the inclusion or exclusion of a component has the same impact on interventions that differ by one specific component. This is expressed in the scatter plot by a line parallel to the line of equality. In our example, we do not observe any parallel line, which indicates that additivity assumption in CNMA may not hold. For a better understanding of the NMA results, it is recommended to apply the leave one component out scatter plot for each component. This tool can be also extended to interventions that differ by a specific component combination and adjusted to use Z values instead of relative effects. An alternative to the leave one component out scatter plot is a waterfall plot, which also displays the interventions that differ by one specific component. The differences in the relative effects of the interventions with and without the specific component are displayed in order to explore if the extra component has a positive or negative impact on the outcome. The direction of the impact, positive or negative, depends on the outcome's nature, beneficial or harmful. Another visualization tool that will help on identifying the most promising components is a component heat plot, which visualizes the efficacy of the 2x2 component combinations. More specifically, each element summarizes the NMA estimates where the corresponding component combination was observed. As a summary measure, the median or the mean can be used. The number of nodes that include the corresponding component combination is also provided in the parentheses of each cell. Letter X is used to highlight any combination of components that are not observed in the network. To identify more easily the most promising components, each element was colored according to the magnitude of its effect. Green color is used to reflect an effect estimate on the desired direction, while red color is used to reflect an effect estimate on the opposite direction. In this example, most elements are green, indicating that the components reduces the level of glycated hemoglobin compared to the control group. However, we are moderate confident about the results because of the uncertainty in the estimates, which is reflected by the size of the gray boxes. The smaller the box, the more confident we are about the finding. Components heat plot can be also adjusted to display Z values instead of relative effects. Similar to the components heat plot is a violin plot in which each violin displays a distribution of the NMA relative effects based on the nodes that include the corresponding component. Therefore, by comparing the violins, we can identify if there are components that are associated with larger effects. The precision of the NMA estimates is also reflected by the size of the dots. The violin plot can be adjusted to use Z-scores and can be extended also to components combinations. Furthermore, by constructing the violins based on the number of components that are included in the nodes, we can explore if the efficacy of the intervention is affected by the number of components. To conclude, we argue of conducting both network meta-analysis and component network meta-analysis when multi-component interventions are present. Also, to supplement the component network meta-analysis and strengthen the network meta-analysis, we can use the proposed tools, which can offer valuable insight on identifying patterns between components and exploring their behavior. The implementation of the proposed visualization tools can be performed by using our recently published R package, namely visconf, which is available on CRAN and also on GitHub. More details about the visualization tools can be found on the original article, Graphical Tools for Visualizing the Results of Network Meta-Analysis of Multi-Component Interventions, published on Research Synthesis Methods. Lastly, I would like to thank my colleagues for their valuable contribution and my supervisor Dimitris Mavridis. Also, the project was supported by the European Union's Horizon 2020 Research and Innovation Program. So, that's it. Thank you for your attention. I'm happy to answer any questions or comments, and of course any ideas or suggestions are more than welcome. Bye bye.
Thanks very much, Georgios. Up next is Chris Pritchard, who's going to introduce some significant updates to the Prisma 2020 package that supports its use as an API.
Hello, thank you for joining us for this talk about the Prisma 2020 flow diagram app and the significant updates that have been made over the past year. My name's Chris Pritchard, I'm the current maintainer of the app, and I'm a senior lecturer in paramedic practice and emergency care in the Institute of Health and Allied Professions at Nottingham Trent University. My colleague Neal Haddaway, who is the founder and organiser of ESMARConf, has also been a great help with this presentation and was the previous maintainer of the package. In addition to myself and Neal, Luke McGuinness did a lot of work at the start in turning a lot of the concepts into reality. And we've also had some additional contributions this year from Hossam Hamadi, who works for Rayan. They wanted to implement a function to enable the app to be called directly from within Rayan. So they did so and contributed the code back to our community, and also to Brennan Chapman, who contributed a feature to enable the app to work with Tibbles as well as data frames. So what is the app for? Well, the Prisma reporting standards were updated in 2020, as I'm sure you're all aware, but within that updated set of standards, there was an updated flow diagram to aid in the reporting and visualization and reviews. And I think they're really important in making it clear where articles were identified and which stage in the process they were excluded or reached inclusion. The reporting standards, when in their update, contain a bit more information than in previous versions of the Prisma statement, and that made the flow diagram a bit more complex. And even before the 2020 update, they could be quite time consuming to create. So no one's idea of fun is sitting around trying to move text boxes on a word processor, but that was often what was needed, was some quite fiddly work. So this app was born. So it provides an R package, so you can use it directly from within R, but also as a hosted Shiny app that requires no coding knowledge whatsoever to enable these flow diagrams to be generated and created, and then exported in the function in interactive HTML. So you can click on links to take you to other parts of a review, but also in PNG, SVG, and PDF formats, for example. In order to actually populate the flow diagram, you can enter values directly within the web app or pass them to the functions themselves. You can use a provided template CSV, or, and this is new for this year, you can call the app directly with some URL parameters to complete the autofill some of the boxes. So over the past year, we've made some significant updates. So there was a big code cleanup last summer, and the automatic calculation of node positions is now part of the app. So instead of relying on manually calculated and entered values for where each box goes, they're calculated relative to each other. This was really needed because otherwise we couldn't move on to the next thing, which is conformity to the Prisma S extension. So for additional reporting standards for the lit review part of the literature search part of your review, by being able to include specific databases or registers, as you can see from the image in the top left, and also then this addition of URL parameters, which enable the app to be embedded more easily within other tools. As I said, Rayan built this into their the premium version of their product, and then contributed the code back to the community. So within the code cleanup, this was done because the code was a bit difficult to read, so lots of functions were perhaps all on one line, which made them a bit harder to deal with, but also had hard-coded figures, for example, for box heights and box positions, variable names that weren't always clear, and also lacked in comments in places. So the code was very functional, it did what we wanted it to do, but didn't really allow for extensibility and building on that to build in new features. So as such, a code review took place. So I used Visual Studio Code and a package called lintar to really support with that. So was able to sort of analyze the source code files and work out what was needed to make them more readable and more consistent. But also within that code review, was able to replace hard-coded numbers and values with ratios and variables. So boxes are positioned relative to each other instead. So that's the Prisma get POS function enables us to do that. And we're also able to programmatically alter the height of a box depending on the number of lines of text in them, which again is really useful because it makes it easier to add new nodes to the package. So if, for example, a new updated set of guidelines was released that required reporting of additional information, that would now be easier to add into this package than it was before. That moves us on to talking about the Prisma S conformities. So the Prisma S extension is specifically for reporting the literature search part of your review, and I'd encourage everyone who's writing up a systematic review to absolutely follow those, but they require the number of records retrieved from each individual database or register. So as you can see, we now have a way of doing that both through the R package and the template CSV, but also from the website. So you can see here we've got each database separated by semicolons, and that creates a nice, straightforward, easy to use package. So that's great. And finally, we can now pre-populate fields in the Shiny app via URL parameters, and I'll talk more about that in the tutorial that I'm going to produce in terms of how that actually works. But the real valuable and exciting thing about this is it means it can be integrated much more easily within other tools and packages, and any numeric field within the CSV file can be passed as a pre-populated field. And I would like to work on passing the non-numeric fields. So for example, those specific databases and registers, I'd like to work on passing them as values in the near future. But for now, it supports any numeric field within the CSV file. Finally, I'd like to talk a little bit about, what the reach of this package is and the impact. So within the hosted version on ShinyApps.io, we use some analytics. They're just aggregated statistics rather than any personally identifiable information. But we can see that this has been accessed globally. And in the last 90 days, for example, over 18,000 unique visitors to the site. So it's a big tool. It's being used by lots of people, and in part that's because it's recommended on the Prisma Statement website. It's part of the editorial guidelines for journal submission in some journals, including BMJ Evidence-Based Practice. But I think the big thing is because it's useful, and I just want to say thank you to all of our users, because if it wasn't used this much, then we wouldn't put the work into making it better. So I just want to say, again, a big thank you for that. So thank you for listening to this talk. As I said, my name's Chris Pritchard. I'm more than happy to take questions via Mastodon or Twitter. And thank you once again for watching.
Thanks so much, Chris. Well, I hope you enjoyed this session as much as I did. The presenters will be online over the next few hours and days to answer any questions that you have, so please keep them coming in. Thanks for attending, and we look forward to seeing you at the next session.